I'm George Hospodarsky. I'm an associate research scientist at the University of Iowa, and I'm going to talk some about the Radiation Belt Storm Probes mission, which is going to launch Thursday morning at 4:08 a.m. hopefully. I'm part of the Electric and Magnetic Field Instruments Suite and Integrated Science team on the Radiation Belt Storm Probe mission. This instrument was built at the University of Iowa, along with parts that were built at the University of New Hampshire and Goddard Space Flight Center. And specifically, I work on the group that built the WAVES instrument. And we measure the wave electric fields from about 10 hertz to 400 kilohertz, and the wave magnetic fields from 10 hertz to 12 kilohertz. Now, what is the Radiation Belt Storm Probe mission? It's two identical spacecraft that are going to be launched Thursday morning, and they're going to study the Earth's radiation belt. And it's part of the Living with the Star program at NASA. The Living with the Star program is basically a program that NASA started to study the sun and why the sun varies, how the sun varies, and how it affects the Earth. And because it does affect the Earth, how does it affect humanity? How does it affect us humans, our technology, things we try to do? And all of it can be tied together into what you may have heard of before called space weather, to try to understand sort of the weather that the sun causes in outer space in the magnetosphere of the Earth. And there's a series of spacecraft that's under the Living with the Star program, along with other spacecraft and other NASA programs, plus the European Space Agency and the Japanese Space Agency also has spacecraft that study the sun and the Earth. But what I'm going to be talking about is the Radiation Belt Storm Probe mission, which launches August 23rd. Related to that is actually a balloon expedition. It's going to be in Antarctica starting in December and January, where they're going to launch balloons. Dartmouth University is in charge of this. They're going to launch balloons in Antarctica. They're going to stay up for weeks at a time, taking measurements of the upper atmosphere at the same time RBSP is taking measurements in space. There's a mission called Solar Probe Plus. It's going to fly very close to the sun, closer than any spacecraft has ever flown to the sun before, to study the sun. And it's supposed to launch in 2018. There's already been a spacecraft called Solar Dynamics Observer, part of Living with the Stars, that launched in 2010, and it's taken data from the sun as we speak. And there's some other missions that are planned for future launches. Now, what are the radiation belts? The radiation belts are two donut-shaped regions that surround the Earth, made up of fast-moving electrically charged particles, electrons and ions and protons. And they're trapped by the Earth's magnetic field. And this is a model drawing of the radiation belts. There's actually an inner belt and an outer belt. And they were discovered by Dr. Van Allen in 1958, the first discovery of the space age. And since Dr. Van Allen was actually the head of the physics department at the University of Iowa at the time, I thought I'd mention a little bit more about him. This is actually a picture of Explorer 1. This is the actual size of Explorer 1 life-size model. So it wasn't a very big spacecraft. The prime scientific instrument on it was a Geiger counter. Basically, he wanted to study cosmic rays in the upper atmosphere. And the payload was up in this top section. This is Von Braun, his team developed the rocket, and also developed the Saturn V rockets. And this is Pickerton, who was the head of the Jet Propulsion Laboratory, who actually built the satellite. Now, Explorer 1 only got data when it was over a tracking station. So it only got little bits of data in parts of its orbit. And Dr. Van Allen, they were seeing these high-energy particles, but they weren't really sure what was going on. So on Explorer 3, which was actually the third U.S. satellite, they put a tape recorder on it. This was the first tape recorder ever flown in space, and it was actually built and designed at the University of Iowa also. With the tape recorder, they were able to get data for the whole orbit of the thing. And with that, they discovered the radiation belts. Specifically, they discovered the inner radiation belt, which goes from about 600 kilometers to 6,000 kilometers above the surface, and it's primarily made up of protons. Later spacecraft also discovered there's another belt called the outer belt that goes from about 10,000 to 65,000 kilometers above the surface. This belt is made up mostly of electrons and ions, energetic electrons and And they were named after him. They were called the Van Allen radiation belts. Now, every planet that has an intrinsic magnetic field has radiation belts. Jupiter has radiation belts, Saturn has radiation belts, Uranus and Neptune. Mars and Venus don't, because they don't have the magnetic field, which is actually what traps the particles. Now, why are we studying the radiation belts? Primarily because we still don't understand them. Even though they were discovered 50 years ago, over 50 years ago, we still don't understand the details of the radiation belt. Especially why sometimes the radiation belts become much more intense. This is a model where red shows the intensity of the belts. This is sort of the normal condition, but sometimes they become much more intense. They fill in the gap between the thing, the inner and outer belt, and the particles become much more energetic. Other times it becomes really quiet. In fact, there's even been times where it's basically disappeared, where we don't see the radiation belts for a short period of time. And then other times they basically don't change, even though a big solar flare storm hits the Earth from the sun. And so one of the prime purposes of radiation belt storm mission is to understand why the belt changes, how it changes, and what causes it to change. So some specific things. Why and how does the energy of the particles change? Why does the density of the particles change? What causes the high speed, as I mentioned earlier, sometimes the belts just disappear. What causes these high speed electrons to just leave the radiation belts and disappear for periods of time? And this can all happen very quickly. In less than a minute at a time, the radiation belts can greatly change. How are the radiation belts affected by the ring current? There's actually an electrical current around the equator of the Earth, which affects the Earth's magnetic field, and it also affects the radiation belts. How do these things interact with each other? There's also other geomagnetic processes that occur, like substorms. How do this all play together? How does the whole magnetosphere work? And are the changes happening only in one region or across the whole belts? Most of the previous studies of radiation belts have been a single spacecraft. Radiation belt storm probe is actually two identical spacecraft that we launched at the same time and fly in different formations during this 2-year lifetime. And one of the things we'll be able to figure out with that is, are things happening just in one location, or are they happening globally? And this just gives you a sort of idea of why two spacecraft. Pretend you're sitting on a big body of water on a raft, and the water goes up. The raft is lifted because the water is going up. You don't know if a wave went by, or if the whole water rose for some reason, or what's going on. But if you have two spacecraft, in this case 2 ducks, and a wave goes by, first one duck's going to go up and then back down, and then the second duck goes up and down. The same thing happens with 2 spacecraft. If a wave comes by the spacecraft, one spacecraft's going to see it first, the second spacecraft later. If both spacecraft see something at the same time, that probably means that something globally is happening over a large area. And it helps a lot, it will help a lot by us having 2 spacecraft operating and 2 identical spacecraft at the same time. RBSP doesn't take pictures. It doesn't have cameras like Mars landers do or anything. What is on this is instruments that measure the particles in space and the waves in space. And this little diagram down here sort of shows some of the interactions that can go on between waves and particles. The penguins on the surfboards are the particles, the electrons or the ions. The waves here are the electromagnetic fields, the magnetic fields. And by the waves, just like on a surfboard, can give energy to the particles. The particles can also give energy back to the waves, or it can damp out the waves. And so what the radiation belt storm probe mission is going to do is study the interaction between the particles, in this case the penguins on the surfboard, and the waves in the field, using 5 different instruments. And they're listed here. The Energetic Particle Composition and Thermoplasma Suite, or ECT, and one thing you learn about NASA is we love acronyms. We love to take the names of things and turn them into initials. The Electric and Magnetic Field Instrument, which is the one I work on, Suite and Integrated Science, which we call EMPHASIS for short, because we don't want to type this out every time we talk about it. That's headed by Craig Kletzen at the University of Iowa. The Electric Field and Wave Suite, or EFW, is led by John Wigan at the University of Minnesota. They study low-frequency waves and DC electric fields. The Radiation Belt Storm Probe Ion Composition Experiment, or RB-SPICE, headed head of the New Jersey Institute of Technology, and the Relativistic Proton Spectrometer, RPS, which was built by the National Reconnaissance Office to study the very highest energy particles. And all these instruments are going to work together to study the radiation belts. Now, why do we care about the radiation belts? The reason we do is that the space weather stuff and the radiation belts affect things that are important to us on Earth. First off, it can affect the astronauts' health. I'll talk a little bit about that in a second. It also can affect the power grids on Earth. There actually was a huge power outage in Canada in the late 70s that was caused by a big solar flare that hit the Earth. And so the space weather can actually cause power outages and spikes in the electrical systems, and we want to try to understand that and figure out ahead of time. But the biggest effect probably is on the satellites that orbit the Earth. For example, the GPS system. How many people have our GPS in their car for this weekend? I have one problem with me. The GPS system is used for all kinds of things. Of course, the Defense Department uses it a lot, but it's used in security systems, it's used for shipping in the airlines, it's used for in your car. Even the power grids, even the stock market uses GPS because they use the clock signals that it sends out at very precise timing. The GPS satellites, made up of dozens of navigation satellites, but they pass through the radiation belts. And when they do, that radiation can affect the electronics. It can damage electronics. Especially when the radiation belts are enhanced. When you have these storms that hit the Earth where the radiation belts become extra strong. And there's actually been communication satellites that were basically destroyed by the radiation belts during a storm where they quit working. When I say destroyed, I don't mean blown up. I mean that some electronics on it quit working and they lost contact with it. And by understanding the radiation belts, we can build better satellites that can withstand them better. We also, if we understand the space weather, we can actually, there are certain things you can do on satellites, like turn off certain systems and stuff if you expect a storm to hit, to improve the odds of them surviving the storm. The other reason we want to understand the radiation environment is for the astronauts and even for airline pilots who fly. Because during a large storm, there's actually an increase in the radiation in space, and even airplanes that fly, especially over the poles, encounter more radiation. Now, it's not enough to be damaging, it's more like maybe a scene you get from getting an X-ray. But if you're a pilot that fly every day, and there's a lot of space weather storms going on, solar storms, that actually can add up over your lifetime of your pilot. And by understanding it better, they actually will, if the storm's predicted to hit the Earth, reroute airlines and stuff to go to less, quote, dangerous areas. Astronauts are pretty safe if they're in a space capsule. The space station has metal around it. It actually shields them from most of the particles. The orbit of the space station is also below the inner radiation belt, and thus is an enhanced period. During an enhanced storm, the astronauts get about a dose into a CAT scan, is what is usually estimated. But if you're in a spacesuit, say on the moon, that's a lot less protection than inside the spaceship. You don't have all the metal around you. And there were actually some studies done, and there were some storms in the 70s that were large enough, or they measured in space, that if there had been astronauts on the moon at the time, in their spacesuit, they probably would have received a very dangerous level of radiation from the solar storm. And so if we're going to send astronauts to Mars, we want to understand how the sun interacts, the whole thing. RBSP is not going to directly do that, but it's one piece of the puzzle to understand how the sun interacts with the Earth and the solar system. And the last thing is just to be able to build better spacecraft. I mentioned that briefly on the GPS thing. But by understanding the radiation belts and exactly how much radiation is involved in them, how much the storm can increase it, what type of particles they are, because different types of particles interact with the spacecraft electronics differently, we can build better spacecraft. Currently, we have crude models of what we think the radiation belts are. And so what we tend to do when we build a spacecraft, we take the model, say this is going to be the worst case, and then we multiply it by 2 or 3 or 10. And then we add that amount of shielding to the spacecraft or change the electronics to handle that. It would be better if we're really not going to see that 2 or 3 times level to put less shielding on it. Because anything you send into space, you want less weight, you can add more electronics, more capabilities. And by doing that, we can build better, more efficient, cheaper spacecraft if we understand the radiation belt better. We also, as I mentioned, we really want to understand the space weather forecasting. Just like you get a weather forecast in the Earth for Earth weather, we'd like to be able to do a forecast, an accurate forecast what the space weather is going to be. Is this solar flare that shot out, is it going to affect the Earth? Is the radiation belts going to get worse? Are the ionosphere going to be active, etc.? Are we going to see northern lights? How many of you have ever seen the northern lights, the aurora borealis? Pretty hard to do in Florida, but in Iowa you can get to see it every so often. If you go up to Canada or Alaska, you can see it much more often. So, in ending, I just want to say the Radiation Belt Storm Probe mission will launch, it's supposed to launch at 4:08 a.m. Thursday morning. So if you're still in Florida, it's worth it to get up, walk outside your hotel room and look to the east or whichever direction Cape Canaveral is. It's a night launch, so if it's not cloudy out, you'll be able to see it from a long ways away. If you're in Orlando, you should easily be able to see it. If you're even farther away, you can still see it if it's clear out. There's about a 20-minute launch window. It goes from about 4:08 to 4:28. And if for some reason it doesn't launch on Thursday, we'll launch sometime later, a day or two later, depending on why it was delayed. And if you have any questions, I will try to answer them. There's a really good website, rbsp.jhuapl, Johns Hopkins University Applied Physics Lab.edu, or also on NASA.gov, that has all kinds of movies, animations, lots of questions and stuff, all about the mission. There's also a booth over by the IMAX Theater building, inside the IMAX Theater building, that has more information, posters, etc. You should stop by and see that. Thank you very much. Are there any questions? Thank you for coming. Yes.
What's the expected life of the mission?
It's a 2-year mission. The spacecraft is designed to last 2 years in the radiation belts. There's always radiation belts have killed spacecraft before, and so there's always that issue. Though I'm hoping many NASA spacecraft last much longer than their expected lifetime. Like the Voyager spacecraft are going on 30 years now. As they leave the solar system, they were designed for maybe 10 years. There's Earth orbiters, MJ, I think actually technically still working. That one's like 40 years old. So we're hoping that much longer than 2 years, but 2 years is its expected mission, lifetime.
I read up somewhere that the magnetic field that causes the whole radiation belt is weakening, and that over time the radiation reaching Earth actually gets stronger. What effect will that have on us?
Yeah, the Earth's radiation belt does change over time, or it has changed over lifetime of the Earth, and it's actually flipped directions at times. And there are different theories that say that it appears like it may be going towards one of these flips where it will decrease for a while and actually change direction. And there could be a period in there where it sort of doesn't protect the Earth as much as it does now. This usually happens over thousands of years, so it probably we won't be able to see a real effect. Most scientists don't think we'll see a real effect for thousands of years or tens of thousands of years. But it is something that some scientists are looking at, and I mean, they do measure the magnetic field, like the North Pole is slowly moving. Actually, I don't remember if it's moving slightly more northward or which direction it's moving, but the North Pole actually moves slightly with time. But that is something, if the Earth's field changes drastically quickly, then we would have issues, because a lot more of this radiation would get into the atmosphere. And would actually greatly affect the radiation belts, because basically the particles bounce along the field lines between the North and South Pole, or region. Yeah, please stop by the booth over in the IMAX building. There's lots of good information there, and other scientists and people that can talk to you too if you have more questions. Thank you very much.
Thank you.